Hey everyone. Today, I want to talk about elementary topology of the complex plane. Now, before we get into that, we first need to define the notion of the distance between two complex numbers. And so, here I have drawn the complex plane and two complex numbers z and w, and I want to find the distance between z and w. And so, the most natural way to define this is to simply take the vector whose tail lies at the tip of w and whose tip lies at the tip of z. And we want to take the length of this vector, right? Because the length of this vector is simply the shortest distance between z and w. And so what exactly is this vector? Well, my claim is that this vector is z minus w, or rather, it's not exactly z minus w, but its length will be the length of z minus w. Now, why is that the case? Well, if we remember back to representing complex addition geometrically, let's say we want to represent z plus w, well, we simply do that by going to the tip of z and tacking on w. And then we find the vector whose tail lies at the origin and whose tip lies at the tip of w. And so what I want you to notice is that z minus w is simply equal to z plus negative w. And so in order to represent this geometrically, all we have to do is simply go to the tip of z and add on negative w, which is w but with its direction reversed. So let's go ahead and do that. So we want to represent z minus w geometrically, so let's go to the tip of z and let's tack on negative w, which is this vector right here. And so z minus w is going to be the vector originating at the origin and whose tip lies at the tip of negative w. So z minus w is this vector right here. And the point z minus w is represented by this point right here. Great. Now, what I want you to notice is that this vector has the exact same direction and magnitude as this vector over here. So if we take the length of this vector that we just found, z minus w, it's going to give us the length of this vector that we actually care about. And so how do we actually take the length of this vector, z minus w? Well, we simply take its modulus, right? Because that'll give us the distance from the origin to the point z minus w, which is right here. And so this is how we define the distance between two complex numbers. The distance between two complex numbers z and w is the modulus of z minus w. Okay, now that we have our notion of distance, we can now define circles in the complex plane. Let z and a be complex numbers and r be a positive real number. The circle centered at A with radius r is defined to be the set of complex numbers z such that the modulus of z minus a is equal to r. So why exactly does this set describe the circle centered at A with radius r? Well, recall from the previous section that the modulus of z minus a is simply the distance from z to a. So this set is the set of complex numbers z that are of distance r to a, which is precisely the circle centered at A with radius r. Great. Now to go over a little bit of notation here, the way we're going to be defining circles here is by using a capital C and then putting the center and the radius in square brackets. Great. Now let's go over a quick example. Let's say we want to represent the circle centered at I with radius 1. How can we do this? Well, as a set of points, this is simply going to be all the complex numbers z such that the distance from z to I, which remember is the modulus of z minus I, is equal to 1, since 1 is the radius. Okay, now let's move on to our next definition. Let z and a be complex numbers and r be a positive real number. The open disk centered at A with radius r is defined to be the set of complex numbers z such that the modulus of z minus a is strictly less than r. Now, what exactly is this set trying to describe? Well, notice that it looks almost exactly the same as the circle definition, except we have a strictly less than rather than an equal to. And so what this is saying is, well, it's all the complex numbers z that are within our distance of A. And so this set is trying to describe the interior of a circle. Great. Now to give you a quick visual example of what the open disk looks like, let's consider the circle centered at A with radius r? Well, the open disk is simply all of the points within the boundary of the circle. And it's important to note that the open disk does not contain any points on the boundary of the circle, since the inequality is a strict inequality, rather than something like less than or equal to. Great. Now let's go over a quick example. Let's say I want to represent the open disk centered at 2i with radius 3. Well, that's simply going to be the set of complex numbers z such that the distance from z to 2i, which is the modulus of z minus 2i, is strictly less than 3. Great. And so just to go over the notation really quick, the open disk is represented the same way as the circle, except with a capital D instead of a capital C. Okay, now we're going to talk about subsets of C and how we can classify points within these subsets. So suppose G is a subset of C. A point A in G is an interior point of G if some open disk with center A is a subset of G. So in order to understand what this definition is saying, let's consider an example. So let's say we have some subset of the complex plane, we'll call it G, and we have some point A in G. So is this point A an interior point of G? Well, if we can draw any open disk centered at A such that that disk fits within G, then A is an interior point of G. And well, in this case, let's say we draw this open disk centered at A. Well, this open disk is a subset of G, so A is an interior point of G in this case. Now, what about an example of a point that is not an interior point? Well, this time, let's put A on the boundary of G, so right here. Can we draw any open disk centered at A such that the open disk is a subset of G? Well, no we cannot, right? Because any open disk we draw is going to have this region of the disk that is not contained within G. And so since we can't draw any open disk centered at A such that it's a subset of G, A is not an interior point of G. And it's actually the case that any point along the boundary of G will not be an interior point of G. Okay, let's move on to our next type of point. Suppose G is a subset of C. A point A in G is a boundary point of G if every open disk centered at A contains a point in G and a point not in G. So let's again think about this using an example. Let's say we have some subset of the complex plane G, and let's say we have a point A in G. So is this point A a boundary point of G? Well, you'll notice that for any open disk that we draw centered at A, there's always going to be this region that contains points that are not in G, and this region that contains points that are in G. And so no matter how we draw our open disk centered at A, these two regions will always exist. The disk will always contain points that are not in G and points that are in G. So this point is a boundary point of G. Now, let's say we draw our point A somewhere over here in G. Is this point a boundary point of G? Well, let's draw some open disk around A and check. Well, are there any points in this disk that are not contained in G? No, there are not. All of the points within the disk are within G. And so that means that A is not a boundary point of G. So those are boundary points. Okay, on to our next type of point. Suppose G is a subset of C. A point A in G is an accumulation point of G if every open disk centered at A contains a point in G different from A. So let's consider another example. Let's say this is my subset of C and we'll label it G. Let's say I have this point in G and let's label it A. Is A an accumulation point of G? Well, we're going to have to check every single open disk. So let's just start with one of them. And let's say that this is the open disk that we're checking. Does this open disk contain points in G that are not equal to A? Well, yeah, this point right here is a point in G, but it's not equal to A. So this open disk satisfies this property. Now, what if we make this disk larger? Well, if we make this disk larger, this point that we already identified as being in G but not equaling A will still be within the disk, since making the radius of the disk larger simply just includes more points than it already does. So making the disk larger doesn't change the fact that the disk satisfies the property. Now, what if we make this disk smaller? Well, if we make it smaller, let's say this is the disk that we're now considering, it doesn't contain this point that we identified, but what about this point right here? Well, that point is within the disk, and it's not equal to A, and it is in G. And so no matter how small we make this disk, we're still always going to be able to find a point within the disk that is contained within G that is not equal to A. So no matter what open disk we have centered at A, the disk always satisfies this property. And so A is an accumulation point of G. Now, what if we have a point that is not an accumulation point of G? What does that look like? Well, in order to show this, we're actually going to have to extend G a little bit. Let's say that G also includes this point over here and this point over here. And let's say that this upper point is A. Is A an accumulation point of G? Well, let's consider this open disk around A. Does this open disk contain any points in G that are not equal to A? No, it does not. Therefore, A cannot be an accumulation point of G. And so the same actually follows for this point down here. We can draw this open disk around this point, and well, none of the points in this open disk are in G that are not this point. Therefore, this point is also not an accumulation point of G. Alright, on to our last type of point. Suppose G is a subset of C. A point A in G is an isolated point of G if some open disk centered at A contains no points of G other than A. So let's go ahead and draw in our subset G of C. And let's say that G also contains these points over here. And let's say that this is the point that we're labeling A. Is A an isolated point of G? Well, let's say we draw this open disk around A. Is there any other point within this disk other than A that is also within G? No, there is not. Therefore, A is an isolated point of G. Now, what about this point? Is this point an isolated point of G? Well, no, it's not, because any open disk that we draw around A is always going to contain points in G that are not equal to A. So this point here is not an isolated point of G. And there are the types of points within subsets of C. Okay, now that we've covered the types of points within subsets of C, we can now move on to some more definitions. And so a set is open if all of its points are interior points. Now, what would be an example of an open set? Well, let's recall back to the open disk centered at A with radius r. And so remember that the open disk centered at A with radius r is the interior of the circle centered at A with radius r. Now, why exactly is this set open? Well, for every point within the open disk, we can draw a smaller open disk around that point that fits within the larger open disk. And the reason we can do this is because the open disk does not contain the boundary of the circle. And so we can get arbitrarily close to the edge of the circle and never quite touch it. And so we can always draw some smaller open disk that fits within the larger open disk, which means that all of the points in the open disk are interior points, and that means that it's open. Great. Now what about another example? Well, let's consider just the entire complex plane. Well, the entire complex plane is open since for any point in the complex plane, we can simply draw an open disk around that point, and the open disk fits within the plane. And so the complex plane must be open. Alright, now let's talk about closed sets. A set is closed if it contains all of its boundary points. And so let's go over the complex plane again. Is the complex plane a closed set? Well, let's first recall what it means for a point to be a boundary point. A point is a boundary point if every single disk centered at that point contains a point within the set and a point that's not in the set. And so what I want you to notice is that every single point in C, no matter what open disk you draw around it, everything in the open disk will always be contained within C. And so that means that the set of boundary points of C is nothing, or the empty set. And so since the empty set is a subset of every set, the empty set is a subset of C, and therefore C contains all of its boundary points. So the complex plane is a closed set. And something weird that you've probably noticed here is that the complex plane is actually both open and closed at the same time. So openness and closedness are not mutually exclusive concepts. And it actually turns out that there's only two sets in the complex plane that satisfy the property of being both open and closed. And those two sets are the entire complex plane and the empty set. And it's actually the case that a set can be neither open nor closed, which I think is pretty interesting. Great. Now let's go over a more normal example. Let's say we have the open disk centered at A with radius r unioned with the circle centered at A with radius r. So this is the interior of the circle and the boundary of the circle. And so we're looking at this set right here. And so since this set contains the interior of the circle and the boundary of the circle, well, it contains all of its boundary points, so this set is indeed closed. All right, now that we've gone over closedness, let's go over the closed disk. Let A and Z be complex numbers, and R be a positive real number. The closed disk centered at A with radius r is the set of complex numbers z such that the modulus of z minus a is less than or equal to r. And so the closed disk is essentially just the open disk, except it also contains the boundary of the circle. And so since the closed disk contains its boundary, the closed disk is indeed closed. And just a little bit of the notation here, the closed disk is represented the same way as the open disk, except with an overbar over the d. All right, a few more quick definitions here. The boundary of a set G, and the boundary is denoted using this backwards curly D symbol in front of the G, is the set of all boundary points of G. The interior of G is the set of all interior points of G. And finally, the closure of G is the set G unioned with its boundary. All right, now let's talk about boundedness. A set G is bounded if G is a subset of the open disk centered at 0 with radius r for some r. And so let's go over an example. Is the open disk centered at 0 with radius 2 a bounded set? Well, if it's a subset of the open disk centered at 0 with some radius r, then it is bounded. And well, let's just replace r with a number bigger than 2. Let's say 3. Well, now the open disk centered at 0 with radius 2 is a subset of the open disk centered at 0 with radius 3. So the open disk centered at 0 with radius 2 must be bounded. Great. Now what about the entire complex plane? Is the entire complex plane bounded? Well, let's draw this out visually. So for any open disk we draw centered at the origin, it doesn't matter how large this disk gets because the complex plane stretches out infinitely in the real and the imaginary directions. So no matter how large we make this disk, the complex plane will never fit within it. And so the complex plane is not bounded. Next, let's talk about connectedness. Two sets X and Y are separated if there are disjoint open sets A and B so that X is a subset of A and Y is a subset of B. A set G is connected if it is impossible to find two separated non-empty sets whose union is G. And finally, a region is a connected open set. And so let's go over an example. Let's say that we have X, which is equal to the interval from 0 to 1 excluding 1, and Y is equal to the interval from 1 to 2 excluding 1. And so the question I want to ask is, are these two sets separated? And if we can construct two disjoint open sets A and B so that X is a subset of A and Y is a subset of B, then X and Y are separated. So let's attempt to make such a construction. So let's say that A is the open disk centered at 0 with radius 1, and B is the open disk centered at 2 with radius 1. And so the first thing we need to figure out is, are A and B open and disjoint? Well, let's draw this out visually. So the open disk centered at 0 with radius 1 looks something like this, and we'll label this A, since this is our set A. And the open disk centered at 2 with radius 1 looks something like this, and this is the set B, right? And so are these two sets open? Well, A and B are both open disks, and we've already gone over that open disks are indeed open sets, and so that condition is satisfied. However, are A and B disjoint? Well, the only possible place that A and B could be touching is on their boundaries, right? And since A and B are open disks, they don't contain their boundaries, and so A and B must be disjoint. So now that we know that A and B are disjoint open sets, the question we need to answer is, are X and Y subsets of A and B? Well, let's consider X first. Is X a subset of A? Well, it's pretty obvious here that A contains all of X. The only point in which A could potentially not contain a point in X is at 1. But since X doesn't contain 1, it excludes 1. Well, the open disk centered at 0 with radius 1 does contain X. And so X is a subset of A. And the same logic applies for Y being a subset of B. And so since we identified two open sets A and B, such that X is a subset of A and Y is a subset of B, X and Y are separated. Okay, so let's continue with this example. The next question I want to ask is the set X union Y connected? And so let's actually write out this set. So X union Y is equal to the union of the interval from 0 to 1 excluding 1 and the interval from 1 to 2 excluding 1. And so this is going to be equal to the interval from 0 to 2 minus the set containing 1. So this is the set that we want to determine whether or not it's connected. And so recall that a set is connected if it is impossible to find two separated non-empty sets whose union is that set, which in this case is X union Y. And well, since X and Y are separated and non-empty, and their union is X union Y, which is this set right here, this interval right here, excluding 1, is not connected. All right, let's now move on to paths. A path or curve in C is a continuous function gamma from the interval from A to B to C, where the interval from A to B is a closed interval in R. And so the way that paths are typically expressed are in two parts. Paths are usually given as a function gamma in terms of t, and as a set of bounds on t, where the lower bound is usually called a, and the upper bound is usually called b, and a and b are real numbers. So this is how we can characterize a path in C, as a function gamma in terms of t, and as a set of bounds on t. A path is smooth if gamma is differentiable and the derivative gamma prime is continuous and non-zero. And as a refresher, the function gamma from the interval from a to b to c is continuous if for all t naught in the interval from a to b, the limit as t approaches t naught of gamma of t equals gamma of t naught. And the derivative of gamma at t naught is equal to the limit as t approaches t naught of gamma of t minus gamma of t naught over t minus t naught. So this is what it means for a path to be smooth. It must be differentiable and its derivative must be continuous and non-zero. Alright, just to give you guys a quick example of a path that is smooth, the path gamma of t equals e to the power it, where t runs from 0 to pi over 2, is a smooth path. And I'll leave the verification of that up to you guys. And so what you have to do to verify this is show that gamma is differentiable on this interval, and then show that gamma's derivative is continuous and non-zero on this interval. So have fun with that. And so something else I want to mention here is that paths always have a sort of direction or orientation to them. And so if we draw this path out, it's going to look something like the portion of the unit circle in quadrant 1. And the way you get that is by using Euler's formula, which is e to the power it is equal to cosine of t plus I sine of t, and just plug in a bunch of points from 0 to pi over 2 and you'll eventually be able to sort of connect the dots, and it'll start to look something like the portion of the unit circle in quadrant 1. And so what exactly is like the direction or orientation of this path here? Well, the path starts at t equals 0, or the lower bound of t. And so if we plug in t equals 0 into e to the power it, we get 1. So the path starts down here. And if we plug in pi over 2, we get I. And so the path runs from this bottom point down here to this top point. And so the path is traveling in this direction that this arrow is indicating here. Something else I very quickly wanted to mention before moving on is that you can also represent a path in terms of real and imaginary parts. So you can also represent a path like gamma of t as a real valued function x of t plus I times a real valued function y of t. And so this is another way you can represent a path, is in terms of real and imaginary parts. The path gamma is simple if gamma of t is injective, with the possible exception that gamma of a equals gamma of b. So what exactly is this definition getting at? Well, in plain English, a path is simple if it does not intersect itself. So let's take this path, for example. This path is simple since it doesn't intersect itself anywhere. However, say we had this path here. Well, because there's an intersection point in the path is no longer simple. And so the reason why there cannot be intersection points given this definition is because this intersection point means that there are two distinct t values that map to the same value in the codomain, which makes the function no longer injective. So this is why there can be no intersection points in a simple curve. Great. Now what about this exception that gamma of a is allowed to equal gamma of b? Well, recall that gamma of a is simply the start of the path, and gamma of b is the end of the path. And so what this is saying is that a curve is still simple if it forms a closed loop like this. To piggyback off of what was just said, the path gamma is closed if gamma of a equals gamma of b. So in other words, if the path ends where it started, the path is closed. And notice that this definition doesn't require that there be no intersections. So say for example, we have this figure 8 path. Well, this path is still closed even though it does have an intersection point. So don't get closedness of a path confused with simpleness of a path. Alright, the last thing I want to go over is a theorem. If any two points in G can be connected by a path in G, then G is connected. Conversely, if G is open and connected, then any two points of G can be connected by a path in G. In fact, we can connect any two points of G by a chain of horizontal and vertical segments lying in G. And so essentially what this theorem is saying is if all of the points in G can be connected via a path, then G must be a connected set. And if G is an open and connected set, then it turns out that we can actually connect any two points using just vertical and horizontal segments. So to give a visual example, let's say this is one of our points and this is our second point. And let's suppose that G is open and connected. Well, then that means we should be able to connect this first point to this second point by only using horizontal and vertical segments. And so here's a way we can do this. Here's a horizontal segment, and here's a vertical segment. And so if G is open and connected, we can construct such a path for any two points in G. And that's it for this video. In the next video, we're going to be talking about limits and continuity.